All right, last bit here from electrostatics. This final section is where we talked about gravitational force, which went back to first semester, and we compared that to electrostatic force. So just recapping on those equations, okay? Um, Gravitational force was a constant g, oops, can't see that, times mass 1 times mass 2 divided by the distance between those two masses squared. So say I've got a planet and a moon. This is mass 1, this is mass 2, the distance between them. And so the force depends on the value of the masses. That's a direct relationship. And then there's an inverse square relationship with distance. Okay. We compared that to the electrostatic force because they're really similarly structured. So electrostatic force has a different constant called K. First charge and second charge divided by, again, the distance between them squared. So let's say we got two charges here. Q1 is this value, Q2 is this value, and then we've got a distance between them. So again, force is directly related to the value of the charges, and inverse square related to the distance between them. Okay. So a couple of different things we did with this. We compared these two just like informationally. So if we look at a few things here, for gravitational force, does it attract or repel or both? Gravitational only attracts everything that has mass is attracted to everything else that has a mass, but there's no repelling that occurs because of mass. Whereas with electrostatic force, we know you can attract or repel depending on whether you're opposite charges where you attract or you are like charges where you repel. Strength of the force, we talked about this in class. In my class, we rubbed balloons and we made them stick to the wall or the ceiling. We talked about how that showed us the electrostatic force is stronger than gravitational force because that force between the charges and the balloon and the wall was enough to keep it on there, overcoming gravity. So gravitational force is much weaker. Gravitational force is really weak unless you're big, huge, massive objects. And that's really because this constant is a super, super tiny number. So, but this is fundamentally like a weaker force than electrostatic force. And then relationship of force and distance between objects. So in this case, we've seen that's the same for these two. In both cases, they've got this inverse square relationship with the distance between them. So I'm going to put inverse square for both of these. And what that means really, is that as distance goes up, the force goes down. They can't exert as much force on each other, whether it's gravity or electrostatic force, if your distance is bigger. Okay. Okay, then we've got these models. We're going to look at these. Are they correct? If not, how should we correct them? So here we see we've got our two masses, our distance between them. This is a gravitational force. We see these two are repelling, okay, based on the arrows, which is not correct. So we need to switch those arrows. To make this attract, okay, because this force only attracts. So I'm going to say no here. And then we're just correcting them as we look at these. So then electrostatic force, I see I've got two sets of charges here. but I see that my opposites are repelling, which it would not be the case. Okay, they would attract to each other. So opposite charges attract. And then like charges repel. So again, we're going to modify these arrows and show that. Okay, so that way we've corrected all those little models. So, all right, and then last one, I kind of wrote all over this and ran out of room, but how would the magnitude of the electrostatic force between two charges or two objects change if the charge of one of them is doubled and the distance is also doubled? All right, so this is a rule of ones. I also called this a factor of change. And so this is an example where you call everything one and then you change what needs to be changed. Okay, so we've got our electrostatic force is our two charges multiplied together divided by the distance between them squared. I'm not going to worry about the constant because it's the same no matter what. Okay, so let's start with everything being equal to 1. If we do that, then our electrostatic force is just 1 times 1 divided by 1 squared. Okay, that seems kind of boring, but then what we're going to do is change it based on the charge of 1 doubled and the distance is doubled. Okay, so we're going to make, so let's say now we'll leave Q1 alone. We'll say Q2 doubled. So now instead of it being 1, it's 2, and then distance is doubled. And then we put these numbers back into our equation and we see how our force is modified. What is the factor of change of our force? So phi equals 1 for the first charge times 2, because that one doubled, divided by 2 for distance, and I have to square that. And that's really important. A lot of times it's easy to forget that. But this is squared on the bottom, and that's a really important part of this equation. So that gives me 1 times 2 is 2. 2 squared is 4. When I simplify that, I get 1/2. So my force is cut in half. Even though one of my charges doubled, doubling the distance between them, because that's also a distance squared, that makes a big impact on the force. So the force value is cut in half when I do that. But with rule of ones, you just start off like so with everything 1, set up your equation, and then change only the things you need to by the factors that they change, multiply it out again, and then that gives you this factor of change of how much your electrostatic force was affected. So, or your force of gravity if you're doing that one. So all right, that's it for electrostatics.